All right, let's work on estimating a standard deviation problem. So I have 40 people from an Atkins weight loss diet program that lost an average of 2.1 pounds. So all of the relevant information I'm going to try to underline in blue. From 40 people, we lost an average of 2.1 pounds and a standard deviation of 4.8 pounds. So in fact, let's go ahead and start writing these down, give them variable names. Let's let n be the number of people that participated in this study. We had 40 people. The average weight loss was 2.1 pounds. And the standard deviation of the sample, so let's say standard deviation sub S for subsample, was 4.8 pounds. All right, so this is everything that we know, and now we are charged with two things. The first, estimate the true standard deviation of people that do this Atkins weight loss diet program to a 90% accuracy. So I want to be 90% sure that the interval that I build contains the true standard deviation of people that, the true standard deviation of the weight loss that people experience from this Atkins weight loss diet. And then two, I want to use that interval that I give myself to see if I can predict how much weight loss I can expect if I were to do this program. Right? Assuming that we aren't too far away from the average, what kind of results can we expect? So let's jump into it. I'm trying to estimate a standard deviation. So I'm going to use a chi-square distribution and make sure to emphasize its non-symmetry. So that way we don't accidentally use symmetry in our work later on. All right. So I'm going to center my curve at the standard deviation given to me by my sample because I'm trying to estimate my standard deviation. So I'm trying to build an interval around this number. And how wide do I want that interval to be? I want it to, let's underline one more thing. I want to use 90%. Right, that's how sure I want to be. So I'm going to collect 90% of the area in the middle, leaving me with 5% to spend there and 5% in the right tail. Okay, so let's write down the equation. The variance of a population is bounded between n minus 1, the variance of your sample, divided by the chi-square value from the right-hand side. And the upper bound is the same numerator, n minus 1, times the variance of your sample, divided by the chi-square left value. So some of your equations might see an s squared there. That's the standard deviation of the sample squared, which is, of course, the same thing as variance. All right, so the variance of the population is stuck between n minus 1 here. I have 40 people, so my degrees of freedom here, n minus 1, will be 39. The variance of my population, so that will be the square of the standard deviation. My standard deviation was 4.8. So then if I take that and I square it, I get a variance of 23.04. 23.04. That's measured in pounds squared now because it's variance. And then we'll figure out our critical values later. Let's fill in the rest of the side, the bound. I've got 39 times 23.041. Oh, no, that pounds is part of the LS. Or sorry, the 1 there is actually the L. So in fact, I'm going to leave off my units. Just 23.04. All right, now let's figure out what these critical values are. So I need from the chi-square distribution, my chi-square right value and my chi-square left value. So just like in proportions and means, anytime we try to find a critical value, we need to look at those tables. So I go back up to this situation that I drew. And for the chi-square right value, so this isn't actually the distribution of the chi-square values, but for just illustrative purposes, here's the scenario. I'm looking for the chi-square left value and the chi-square right value. And the chi-square left value has how much area to the right of it? Because from my table gives me areas to the right of critical values underneath the chi-square distribution. So the chi-square left value has 90 plus 5, so 95% of the area to the right of it. So from my table, I see that my chi-square left value is 20, or sorry, the chi-square left value is over here. Chi-square left value is 26.509. Now to find the chi-square right value, go up to my picture. Chi-square right only has 5% of the area to the right of it. So from my table, the chi-square right value that has 5% of the area to the right is 55.758. Oops, I forgot my bound there. So the variance of all people that do this weight loss diet is going to be, with 90% accuracy, somewhere between 16.1154 and 33.8964. Now, our data only measured out to 2.1 to the 10th place after the decimal. So when we get a bound for our standard deviation, right, I can get a bound for my standard deviation of the population by just taking the square root of everything. So the square root of 16.1154 is going to give me 4.014. And the square root of 33.8964 gives me a standard deviation of 5.822. Now we only measured out to the 10th place. So let's go ahead and give these a bound. .8 and 4.0. All right, that is our interval with 90% confidence for the population standard deviation. Now, I forgot to mention up here when I was getting my critical values that 39 is the degrees of freedom, and that doesn't appear on our table. So I just estimated and took the closest critical value that I could and used degrees of freedom to be 40. Right. Okay, let's ask the second part now. I think we've satisfied the conditions for number one. We've estimated the standard deviation with 90% accuracy. Now, if we are not an outlier, how much weight change can we expect? All right, so what we just told ourselves is, let's get a picture of this. My standard deviation at its smallest with 90% accuracy is about 4. Right, so if I was to draw the normal curve around the weight loss, it would look something like this, centered at the average that I got from my sample. At worst, it's more spread out, right, with a higher standard deviation. So this is probably exaggerated, but this is what you need to think about. When you have a small standard deviation, your data is more centrally localized. When you have a larger standard deviation, it's more spread out. So if we were to draw the distribution of the average weight loss, let's assume the worst case scenario. Worst case is our data is more spread out and we are less certain of where the actual true average is. So I'm going to center it at 2.1 because my average weight loss was 2.1 pounds. Now, if I'm not an outlier, remember from the beginning of the class, we defined an outlier as being 2 standard deviations away. from your mean, just as a rough idea of an outlier. And at worst, our standard deviation is 5.8. So if I take 2.1 and I move 5.8 twice to the right, I get an upper bound of 13.74 pounds. And if I move to the left twice, I get a lower bound of minus 9.54. So what does this mean? It means that if I'm not an outlier, if I'm no more than 2 standard deviations away from the center, then I could expect to either lose 13 pounds, or if I negate losing 9 pounds, that's me actually adding 9 pounds. So this could give you a little bit of benefit if you decide to do this program or not. Because of the variation in the sample, you're not really sure if you're actually going to lose 13 pounds. But you could gain 9 pounds. Right? The data is just too spread out for you to be able to make a more of a concrete estimate than that. Okay, hope you found this helpful.